Hello class. Our discussion today is going to be on alkynes. So we recall that alkynes look like this. And so we need to understand some special features about this molecule so we can gain a better appreciation for why it's reactive, because what we're going to be discussing is how do alkynes react with other reagents. So the first thing that we see is we need to know where these electrons are coming from. So one of those bonds right there is going to be our sigma bond. And then we have, are these going to be color-coded drastically different? I put a blue bond up there and a pink one down here. So in an alkyne, we have a green bond in middle, which is the sigma bond, and then we have two pi bonds on top and bottom. And so what does that do when you look at the orbitals of this molecule here? When we take the green marker here, let's put it right here. What does that sigma bond look like? Well, it's going to be what type of orbital is it going to be? Remember the hybridization state of this guy? So this carbon right here has one electron group, two electron groups. So that's sp hybridized. So we're going to have the other carbon over here, and it's going to have the p orbitals, the sp sigma bond right there, and then you'll have the two electrons right there. So I'm not going to represent the electrons because it's just going to messy up the image here. Okay. So this bond right here is the sigma head-to-head overlap, which is the green one. And then what we have is the blue one is going to form a pi bond from p orbitals. So I'll draw a p orbital there, p orbital there, p, p. And these have phases. Okay. And so we have overlap of electron density above and below. But what's really, really important to understand is that these pi orbitals are perpendicular to this axis right here. All right. So if this molecule in green is in the plane of the glass, then what do we have? Then we have the p orbitals. Well, let's take the alkyne, right here, and represent it by my hand. All right. So my hand represents the green atoms there. The blue p orbitals are going to be above and below my hand. Okay, so perpendicular. But then what we have is the pink pi electrons here, or pi orbitals. And they're going to be perpendicular also, but and these are a little harder to draw. Okay, because if my hand represents the green molecule, the blue is above and below, but the pink is going to be out or into the glass and out of the glass. Okay? And it's going to have, and those are going to also have phases, and there's going to be overlap right there. And that's going to cause us to have a triple bond. Now, because these two carbons are sp hybridized, you see the bond angle between the two? When we look at the central carbon here, that bond angle right there is what? 180 degrees. And at 180 degrees, it is nearly impossible. No, I don't want to say this. There's very few exceptions to this rule. You cannot incorporate an alkyne into a ring structure. So if we wanted to have a 5-membered ring but turn that guy into an alkyne, that's not going to happen. Why? because look at that bond angle right there. That is deviating drastically from this 180 degree. And so that just does not happen. Okay. Some other features of an alkyne are the bond lengths here. The bond lengths between the triple bond and the bond lengths between the R and the carbon. And so what I'm going to do is erase this board and draw 3 molecules that we're going to look at their bond lengths and make some comparisons. So what we have here is ethane, ethylene, and acetylene. You all see that they have 2 carbons each, right? So what I want to first focus on is the bond lengths. In ethane, the bond length between the 2 carbons, that's the largest or the longest. And the distance between these 2 carbons right here is going to be the smallest. Now, why is that the case? Well, one reason is its hybridization state. These carbons right here are what? sp3 hybridized. This one's sp2, and that is sp. So it's hybridized, right? So what are we doing? We are taking our orbitals here. Let's see here. 1s. So that's our 2s, and that's our 2p orbitals, right? Like that. And when we hybridize it to a sp3, what we're doing is we're going to take 1s orbital and 3p orbitals and hybridize it to the same energy. So that's our sp3. And so then that's what the electron configuration would look like for carbon here. It's sp3 hybridized. We have those 4 atomic orbitals. Now what's interesting about the sp3 is it has only 25% s character. Why is that? Well, we have 1 s orbital and 3 p orbitals, and we mix them together. So when we come over here, the shape is technically 25% s. Remember, an s orbital is spherical, and then a p orbital kind of looks like dumbbells. So when we hybridize these two to get these guys, it's going to look 25% like an S and 75% like a P. Not a full P and not a full S, but a hybrid of the two. Now, if we contrast that to the alkyne over here, what's that hybridization state going to look like? Well, we said it's only an sp. So what we're doing is we're only going to hybridize, take 1 s and 1 p orbital and hybridize it together. So we're going to get 2 of those. Both of those are sp. We took 1 here, and then left the other 2 p orbitals alone. So that's a p and that's a p. And then when we put our electrons in there, now why am I only putting 4 right here? It's because carbon has 4 valence electrons. So we are trying to understand here how carbon is bonding, and it bonds like this in a sp hybridized format. Okay, so when we look at an sp, what do we have? We have 50% S and 50% P. So that means that this hybridized orbitals right here looks basically 50-50 of this. And we have learned from general chemistry that if you have a complete s orbitals, the electrons are going to be closer to the nucleus. Whereas in a p orbital, the electrons are further away from the nucleus. Okay. And a p orbital is longer than a s. And so when we look at the ethane, sp3 hybridized, it's going to have a longer bond because it has more p character. Or the way the textbook says, it has only 25% s character. In contrast, the acetylene or the alkyne is a 50% s. So that means those electrons right there are going to be, or that bond is going to be shorter because it has more s character. Also, why does this molecule have a shorter bond? Is because it has more s character, so the electrons are closer to the nucleus, and so it sucks the bond in. Because the electrons are closer to the nucleus, it's going to shrink the length of that bond. There's more attraction for the electrons to the nucleus. And then here, our ethylene right here is just smack dab in the middle of that spectrum there. But what would, to finish this out, what would the electron configuration look like for ethylene? Well, we already know the hybridization state, right? sp2. So that simply means we're taking one s and two p's, and we're going to hybridize those. So those are sp2, and then we're going to just not touch one of the p's. And so now we have the 4 valence electrons there, and you can see now how much s character do we have right here? 1 out of 3 is 33%. So we have 33% s character for sp2 hybridized carbons. Now this hybridization state not only affects the bond length between the two carbons here, but the hybridization state is also going to affect the bond length of the hydrogens. So I'm just going to draw one. Yeah, let's draw them all right there. Okay, so we have those 3 hydrogens. And we can draw those out there. And that one's already drawn out there for the alkyne. We can also say that this carbon-hydrogen bond length versus that one and that one follows the same trend. This one is the longest. This one's the shortest. Why is the carbon-hydrogen bonds shorter for a alkyne? It all comes back to the shape of those orbitals. More s character, so the electrons are closer to the nucleus, so those bonds just shrink in and are held tighter to each other. The electrons in this hydrogen and in this carbon, they're just held together more closely, so that bond length shrinks. Let's see. Another interesting feature about alkynes is the acidity of the terminal hydrogens here. When we compare an alkane versus an alkyne and an alkene, the alkanes are the least acidic. This carbon hydrogen right here, or that hydrogen right there, it's the least acidic. How acidic is it? Well, it has a pKa of around 50. Not acidic at all. An alkene has a pKa of around 44. So not, I mean, that's 6 orders of magnitude difference. So what's that? A million times? So an alkene is a million times more acidic than that guy. But look at an alkyne. It has a pKa of about 25. I'm going to see if we have another marker. Let's see if this one's a better one. That one looks like there's more ink in it. So we need to understand why that's the case. Why is an alkyne more acidic? So let's just go back to acid-base chemistry to look at this again. Because what's going to happen if we have an acid and we have a base, how does it work? Well, the base is going to come and grab the proton and give us our conjugate base plus our conjugate acid. All right. That's what's happening. So when we take a look at an alkyne, what's happening? We're going to have some kind of base. And this base has to be a strong base. And I'm going to show you one in a moment. So that's going to come, grab that proton, and then give us our conjugate base. That looks like this, plus that, our conjugate acid. So that's what we want to do. We want to compare, why is this guy not acidic, and this one is orders of magnitude more acidic than the alkane, which is kind of interesting. Well, it comes down to the hybridization states again. What's the hybridization state of this carbon? sp3, sp2, and sp. And we've learned that sp is what? 50% S. So when we take and form this species right here, and this negatively charged species has a name, and it's called an acetylide ion. And you guys know I'm the world's worst speller, so let's make sure I get this right. The acetylide ion is when you start with this and turn it into that. Okay? Now, why is that? Well, how do we compare acidities? Like, what are we actually doing? Well, we're looking at the conjugate base. If the conjugate base is stable, then the acid is acidic. So we have to rationalize and understand, why is it when we take a alkane like this, have our base come and abstract that proton and get something that looks like this, negatively charged. So that means that the lone pair, we have a lone pair there and there. Well, that lone pair has to be in a orbital. Which orbital is that lone pair going to be in? Well, if we draw it, we'll draw what is it going to be? An sp3 hybridized orbital. And we can put the electrons there. But with the acetylide ion, what's the hybridization state? We started at a sp. So we have a sp hybridized orbital here, and it has more S character. So I'm going to kind of just draw it for drastic effects here, okay? Just see now that lone pair, if we put them in that orbital, are closer to the nucleus. It has more S character. And so this conjugate base right here is more stable than this conjugate base because the electrons are being stabilized because they can get closer to the positively charged nucleus. It's a stabilizing effect. And so what we're seeing here is another idea called effective electronegativity. And it's mostly on the board. So effective electronegativity is, well, let me tell you what it's not for a moment. When we look at electronegativity, we go to our periodic table and we see trends like, okay, an oxygen atom is further right than a carbon, so it's going to be more electronegative, right? But when each of these atoms right here is a carbon, we can't go to the periodic table and look at for trends, right? Because it's just carbon, carbon, carbon. So there's that term effective electronegativity, which is saying that a sp hybridized carbon is going to be more electronegative because it can stabilize that negative charge better. Electronegativity is wanting electrons, right? And it can suck those electrons closer. So sp hybridized carbon, it's more electronegative than a sp3 hybridized carbon. Really cool stuff. Let's see, and this right here, the whole concept now, because this is so much more acidic than alkanes, we can do reactions with alkynes because of the acidity difference here. Now you can have alkynes that don't have two hydrogens on either end, like this. Here would be a terminal alkyne. And you could have and form this anion right here. And this has a name, alkynide ion. The one when you have two hydrogens, it's the acetylide. Am I saying that right there? Acetylide ion versus a alkynide ion. Okay, same mechanism, whatnot. What I want to talk about is the base that is used. Is really, really important. It has to be a strong base. And some good bases would be sodium amide. Now, why would that be such a strong base? Because look at it. We have a metal here. That is not a covalent bond. So what we actually have is something that looks like this. You see that nitrogen atom, very basic, has a negative charge. That's a strong base. We also have, let's see, sodium hydride. Another sodium, right? So what does that actually look like here? It's ionic, right? So we have a hydride. When we have just one hydrogen and it's negatively charged, we call it a hydride. And that is very, very basic. And it's a strong, strong base. And then you can even have some bases where it's carbon-based. Like this, where you have a carboanion. And that species is very, very, very basic. But would hydroxide or sodium hydroxide be a strong enough base to do this reaction? That's what I want to demonstrate to you right now. Which ones, because that's a strong base, is it not? By definition it is. But is it strong enough to take off that proton? All right. So just so we don't get confused here, the answer is this one is not strong enough, but the other three that I talked about, sodium amide, sodium hydride, and these carbanion species, those three are strong enough to take off that proton. This one is not. Why? Well, we have to look at equilibrium for that. So we've done acid-base chemistry, so we're going to do this, something that we've already done before. So if we put our sodium amide in here, negatively charged here, so that's the base, so that's going to turn that into ammonia, right? So what we have to do is look at the pKa values of each acid. What's the pKa of this guy? Approximately around 25. Look at the conjugate acid over here. What's the pKa of an amine? Approximately 38. So at equilibrium, which side is going to be favored? Well, it's always pointed in the direction of what? The weaker acid. So this is weaker than that acid, so equilibrium is going to favor to the products. So that base is strong enough to deprotonate this alkyne. But if you change that up a bit to, let's say, the hydroxide, like so, and then what would we get over here? We would get water. What's the pKa of water? About 16. Now when we look, where's the weaker acid? This one. So it shifts equilibrium to this side. So it's equilibrium favors reactants. So we are never going to get enough of our alkyne ion here to do the reactions, because now when we have this species right here, what is that? Well, that's a negatively charged species, right? So that could act as a nucleophile or a base. We've converted this alkyne into a reactive species when we have deprotonated it. So the moral of the story, yes, hydroxide is a strong base, but not strong enough. Do you recall if we took a alkyl halide, like so, and let's make those R groups actually, and let's go R, another set of R groups right there. Remember, we could take a strong base right here and do a E2 reaction where we're going to eliminate the bromine, which is a good leaving group, and so we would generate a alkene. Remember that reaction that we've gone over? Well, we can do the same thing, but when we have two halogens on the carbon. So we could have something like this. Hydrogen, another hydrogen, R group. Now we have two halogens, like this. Now, that guy is an alkyl dihalide. Alkyl halide, dialkyl halide, because we have two halides, right? Makes sense. We can do the exact same mechanism as above now. We can add a strong base. We do an E2 mechanism, and we are going to now generate our alkyne. It's just now we're going to do this reaction actually twice. We're going to do one E1 mechanism or reaction, and we will generate an alkene, and then we'll do it again to form the alkyne. And I'm going to show you the mechanism of how that works. But when we have a dialkyl halide where the halides are attached to the same carbon, we call that geminal. So we could also say this is a geminal dialkyl halide. If we change it up a bit, well, let's work with the geminal first, okay? So let's look at the reaction of a geminal dialkyl halide. So when you have your dialkyl halide, what you have to make sure that you have is on the adjacent carbon in which the halogens are attached. So you see these halogens are attached to this carbon. You have to go to the adjacent carbon, and there has to be two hydrogens. Okay? There has to be at least two. Now, what's happening here is we add some sodium amide, and that's going to act as a very strong base. You need a very strong base. So it's going to abstract one of these two protons. Then it's going to break that carbon-hydrogen bond, and then eliminate one of the halogens. So that's going to generate a carbon like this. Okay. And we'll have our R group, our Br, double bond C, R, H plus our bromide. Okay? And then we're going to take a second equivalent. So that's the first equivalent. Then we will have a second equivalent of sodium amide in our reaction. And so we're going to take that second one and going to come in and subtract that proton, break the carbon-hydrogen bond, go like that, and then kick off the bromine. And now what have we generated? We have generated our molecule like that. Okay? And so there's our alkyne, just like that. Pretty slick, right? Now what happens? Now what we can do is, let's see if we can keep some arrows here. Let's replace, now we can have a dialkyl halide like this, where you can see we have 2 carbons with a halogen. All right, that's interesting. And so what's going to happen here is this guy is also a dialkyl halide, but it's called a vicinal. It's a vicinal dialkyl halide, and that's when the halides are on separate carbons. Now, the halides have to be on 2 carbons that are adjacent to one another. Okay, that's really important. You can't just have a long molecule like this, okay, a bromine over there and a bromine over here, and call those vicinal dialkyl halides. No, vicinal means that they have to be right next to each other. So that is vicinal. That is not. And if I change this one, get rid of that for a second, and if I put a bromine there, then that would be geminal. Okay. So here's our vicinal. So how would that mechanism work? Well, we would have our first equivalent of sodium amide doing the same thing. Perfect. But what's different on the product side here? All right. We said this bromine is right here. All right, so now I have a hydrogen there. So when we have our second equivalent of sodium amide coming in to react, what's it going to do? It's going to come in and grab that proton, go like that, to give us what? The exact same product. So it doesn't matter if you had a vicinal dialkyl halide or a geminal. When you treat it with a very, very strong base like sodium amide, then you're going to get to a alkyne. Same product. Isn't that pretty cool? But when we do this reaction, 2 equivalents of sodium amide is not enough. Not enough at all. Okay. It has to have 3 equivalents. 3 equivalents, okay? That is, well, let me make a distinction here. How do I want to say this here? Okay, let's write this out here. So if you have a dialkyl halide, okay, vicinal or geminal, okay, let's draw our geminal one. Okay, like that. Well, and we add 2 equivalents of our sodium amide. What are we going to get? We are going to generate this product, right? And that is what? A internal alkyne. Okay? But if you are making a terminal alkyne, so if our starting materials would look like this, all right, what you're going to have to do is you have to add 3 equivalents of sodium amide. Because what's going to happen? You're going to generate a terminal alkyne, right? So when the end product is a terminal alkyne, you have to add 3 equivalents of sodium amide. Okay? But when you're just making an internal, you only need to add 2. We're going to see why in a moment. Before we get into why we need 3 equivalents, I want to make sure we understand the reagents here. The standard protocol here is sodium amide in ammonia. So we got to add that other piece to the reaction scheme here. So we have sodium amide in ammonia to get this reaction to proceed. Now, why do you need 3 equivalents when you have a terminal alkyne? Well, this is really cool because what happens after you do the first elimination? All right, so let's look at this mechanistically here. I probably didn't need to erase all that, but oops, I did. So I'm just going to represent it with a B for strong base right now. That's going to represent the sodium amide, okay? So what's the first step in the mechanism here? Well, the base is going to come in and grab a proton, right? And give us, well, that's a horrible, we're missing one of the mechanisms, huh? All right, here. So there we go. That's a better mechanism. And then we're going to have R, carbon, Br, like that, right? And a double bond. And then we can do the second reaction, right? So that's our first equivalent. Then we can do it again with another base. Do another E2. So that's going to come in and grab that and give us our alkynide species right there. All right. No. It's going to give us that guy right there. Okay? So now we've already used 2 equivalents, right? Now, if we could just visualize this reaction in a beaker, and in the beaker we tell the molecules only one at a time, okay? Only one at a time, only one molecule reacts with this, and then this molecule reacts with this to get that, okay? If that's the case, look at what's going to happen here. But we know it doesn't happen, right? If we form one terminal alkyne right here, okay, and after we've used these bases, there's still going to be a lot of base left over, right? That's acidic. And so once you form this, all the leftover, the 2 equivalents of base that are meant to react with all the other dialkyl halides are going to be used up because of this guy. So let's just look at it in rounds. So this reaction is round 1, right? So now let's do round 2. So we're going to have a second dialkyl halide. Okay, so this is round 2. We still have our base present. All right, still have our base present. But now in round 2, what does round 2 have that round 1 did not? This base is now conflicted. It could come and grab this guy and start the process over again. Or this base is like, hey, I see a very acidic proton over here. And so you can't stop that. And so what's going to happen is if you've only added 2 equivalents of base, you have 2 equivalents, or you have all of your dialkyl halide that you want the 2 equivalents to react with. So you've added, okay, if you've added only 2 equivalents of base, those 2 equivalents had to go all to the dialkyl halide. But now this reaction isn't going to go to completion, because if you only put in 2 equivalents of base, you did not account for that you have this as competition. And you're going to run out of base very, very fast. So what you have to do is to add 3 equivalents of base. And what's 3 equivalents of base going to do? It's going to deprotonate all of your product right here. Okay. Basically, when you look at this reaction, you have to have an equivalent of base for this proton, and that proton. So you need 3 equivalents of sodium amide, or the strong base that you're choosing to use for your reaction, when you have a terminal alkyne. Now, if that is no longer a terminal alkyne, you only need 2 equivalents because there's no acidic hydrogen. I hope that makes sense, okay? Let's see here. What do we want to talk about next? So after you add your 3 equivalents here, okay, that's R, that's BR, okay. So how would we do this reaction? We would write it out like this. We would do 3 equivalents of our sodium amide in ammonia. Okay. And what is that going to actually give us? It's going to give us this species right here. The acetylene, no. What is this? It would be this guy right there. There's our alkynide ion. That's what this reaction is going to do. So what we have to do is what's called an aqueous workup, where you can just add some water, hence aqueous workup. And what we're doing is we're working up the reaction. We're going to take this piece, add it to some water to do a proton transfer step. And that proton transfer step is going to put the hydrogen back onto the alkyne. So that's a simple proton transfer, right? So that would just be that negative charge. We have some water, oxygen, and we could have a proton transfer. That would give us our product. Markers are extra squeaky today. All right, so that's all, and we've already determined that hydroxide, right, cannot deprotonate that, so that's good. So really, when you want to do this reaction, you have this step, and then you have a aqueous workup. And sometimes you could see the reaction written like numerated, like we have reaction 1, which is all that, and then you would have reaction 2 shown like that. And then it would just go right to the product. All right? Things to be aware of. The next reaction that we want to talk about is we can also take alkynes and alkenes and reduce them to an alkane. So if we have an alkene, we could treat that with some hydrogen gas and some kind of metal catalyst. So we could use nickel, or we could use platinum, or we could use palladium. You don't have to use all three at the same time. One, you just pick one, it does not matter. Hydrogen gas, and what are you going to generate? You're going to generate an alkane. So you can see that there's one hydrogen there, one hydrogen there. And if we label those carbons 1 and 2, what has happened? We have added a second hydrogen to both of those carbons. And this process of reducing this double bond, because reduction also means when you are adding hydrogens, that's a reduction. But this reaction is also called a hydrogenation. Hydrogenation reaction. Have you ever heard of hydrogenated oils? Well, that's what's happening. Is we're taking oils that have alkenes in them and we are adding hydrogens to them, like that. But we can also take a alkyne as well. We can take an internal alkyne or a terminal alkyne. It does not matter if you treat it with the same reagents. So let's actually do a better example here. Let's draw one with, let's see, 1, 2, there we go. 1, 2, 3, 4. 4 carbons. And if we treat this terminal or internal alkyne with the same reagent, we're going to get the same exact product. But now what has happened, if we call that carbon 1 and that carbon 2, here they have 0 hydrogens, but now we've added 2 of them, like that. So we can hydrogenate an alkene or a alkyne. But one cool thing about alkynes is that if we use this condition right here and pick one of these metals, we'll go all the way to the alkane. But if we take one of these metals and we poison it by adding poison, okay, we're going to get what's called a poisoned catalyst. And a poison catalyst is going to take an alkyne, right, like this, and not go all the way to a alkane, but it will stop at the alkene. And the alkene that it stops at is very, very important. It's going to stop at the cis. It does not make any of the trans alkene. It's predominantly cis. So what type of poison catalyst could we do? Well, there's one that's a very famous one called the Lindlar's catalyst. And I want to spell the name right here. If we do Lindlar's catalyst. So if you take an alkyne, treat it with hydrogen gas, Lindlar's catalyst, you will generate a cis alkene. And Lindlar's catalyst is simply, you're going to use palladium, right? So you take palladium and you mix into that palladium the poison, which is going to be calcium carbonate right there, and trace amounts of lead oxide. Right? So when you take, if it's just the pure palladium, and hydrogen. It's a very active and just an amazing catalyst. It's just going to take the alkyne or alkene all the way to the alkane. Awesome. But if you can make it an okay catalyst, but not as good, we can slow it down. And so it's going to stop at the alkene. And so Lindlar's catalyst is simply a palladium catalyst that's been poisoned with calcium carbonate and lead oxide. Okay, that's very, very, very important to remember the stereochemistry. Because what we can also now do is we could take the same alkyne right here and treat it with a different metal. So we could treat this guy right here. We could treat that with sodium metal, solid sodium metal, okay, in liquid ammonia. And in order to do liquid ammonia, you have to get this pretty cold. So it's going to be a cold reaction here. And look at this is so cool. This is so fun. It is going to stop at the alkene as well. But where does it stop, or what's the stereochemistry? It is going to give us trans. So now we have the ability to select for what type of alkene that we want in a particular product. Do we want an alkene that's cis? If we do, then we use Lindlar's catalyst. If we want our alkene to have a trans bond here, then we are going to use sodium metal dissolved in liquid ammonia. And that reaction is called a metal dissolving reduction. Okay. I think that is just fun and so interesting to me, that you can control the stereochemical outcome just based off of the reagents that you're using. Now, why is this the case? Well, the mechanisms can help us figure that out. Okay, but that's where I'm going to end this video for today.